Welcome back to another video. So in this video, we're going to find the Galois group of the polynomial x to the fifth plus x squared plus 1 over the finite field f2. So this is an interesting problem because we know a property of finite fields, which is that a finite extension of a finite field is automatically a Galois extension. We can use that to find the Galois group in this case. So the first thing that we want to show is that g of x is irreducible. If it were reducible, it would be divisible by some lower degree polynomial. So it would either be divisible by a linear polynomial, a linear factor, or it would be divisible by a quadratic factor, or it would be divisible by a cubic factor, but that would force it to be divisible by a quadratic factor because the total degree is 5. So we're basically just interested in, is this divisible by something linear or is it divisible by something quadratic? And we want to rule out both of those cases. So the reason that g of x isn't divisible by a linear factor is because it has no roots. You can easily see that g of 0 is equal to 1, and you can easily see that g of 1 is also equal to 1 in f2, and neither of these are equal to 0, and these are the only two elements of f2 that you can try. So this is definitely not, this polynomial definitely doesn't have any roots, so it's not divisible by a linear factor. If it were divisible by a quadratic factor, it would have to be divisible by a quadratic that was itself irreducible, again, because g of x has no roots, right? So if there was a quadratic h of x, and h of x divided g of x, you know g of x doesn't have any roots, so h of x had better not have any roots either. So h of x had better be irreducible. And, you know, we can assume that h of x is monic because g of x is monic. So basically, you're just asking what are the monic irreducible quadratics in f2, and do they divide g of x? Well, so basically, because f2 only has two elements, each of these numbers can only be one of those two elements. So each of these can only be 0 or 1. So the only candidates for polynomials here would be x squared plus x. Okay, well, you can immediately see that that's reducible, so that's not going to work. Another possibility would be x squared plus 1. But x squared plus 1 has 1 as a root, so that's not going to work either. Another possibility is x squared, which obviously doesn't work. And so that leaves you with x squared plus x plus 1. So this is a monic irreducible quadratic. Okay, so does x squared plus x plus 1 divide g of x, question mark? Let's show that it doesn't, and let's do that using long division quickly, because this is maybe not the most interesting part of the problem. So x to the fifth plus x squared plus 1. And let's see if this divides into this. So using long division, you would have to multiply by x to the third to get x to the fifth in front. If I multiply this by x to the third, I get x to the fifth plus x to the fourth plus x to the third. And if I subtract those in f2, -1 is equal to +1 in f2. So I have x to the fourth plus x to the third plus x squared plus 1 left over. X squared times x squared equals x to the fourth. So I get x squared here. Here I have x to the fourth plus x cubed plus x squared. And now I have an issue because if I subtract these, I just get 1. And 1 is a remainder that isn't divisible by x squared plus x plus 1. So this division does not work. Okay, so what this shows is that g of x, which was x to the 5th plus x squared plus 1, is irreducible because it has no roots and it's not divisible by a monic, irreducible quadratic polynomial. So in some sense, this next part is the easiest part of the problem, because let's just take any root of g in a splitting field, and let's just adjoin it to f2. And what's nice about this is we automatically know what this is isomorphic to, because g of x is irreducible. So if we adjoin a root of an irreducible polynomial, we get an extension which has degree equal to the degree of the polynomial. So we get a degree 5 extension of f2, and because finite fields are unique up to isomorphism, that has to be f32, because 2 to the 5th is 32. Okay, so we've adjoined one root, and we've gotten a finite extension of a finite field. So the extension f32 over f2 is finite. But that's nice because a finite extension of a Galois extension, a finite extension of a finite field is a Galois extension. Okay? It's a Galois extension. And in addition to it being a Galois extension, it's generated by a single automorphism. In other words, it's cyclic. And again, this is something that's always true for finite fields. If you have a finite extension of a finite field, it's a Galois extension, and it has a cyclic Galois group. Okay, so because this is a Galois extension, the size of the Galois group equals the degree of the extension. So the size of gal, just writing this out, f32 over f2, the size of that is equal to the degree of the extension, which is 5. And it's a cyclic extension. And there's only one cyclic group of order 5. And so therefore that has to be the Galois group. And this is reasoning that you can use for finite fields. It always works if you start with a polynomial that's irreducible, and if you're able to show that it's irreducible, because then you can use the same reasoning that we used here to argue that the extension is a Galois extension, and so therefore it's automatically cyclic, and the order of the extension. And that's the end of this exercise. Thanks very much for watching.